Hey guys, and welcome to your next C++ in game tutorial. Today we are going to be making an artificial intelligence that can play AI perfectly. Now what that means is it can never lose. It will only win or draw. If you take two of these AI players and have them play each other, it will always result in a tie game. And Tic-Tac-Toe is a very simple game, and it's a game where that is completely possible. And we can do it with an algorithm called the Minimax algorithm. Now before we get into that algorithm and how it works, let's go ahead and just see what I have so far. I've actually made us a little template project. Go into the description and you'll see a link to download this. I want you guys to go and download that and take a look at the code. I've commented it pretty well. It's a better tic-tac-toe game than the previous one we made. So make sure to look through it and make sure you understand at least how most of the code works. And if you have any questions about it, just ask me in the comments and I will be happy to help you out. So right now there is no single player, so multiplayer is going to be yes. So let's go ahead and see how this works. We can just type the x and y coordinates and that will place our little x or O. So it's x's turn, he's going to go in the bottom left hand corner. Now it's O's turn, he's going to go in the middle. Or no, we'll say the bottom middle. Then x will go in the middle. Then we'll say O goes in the bottom right because he's not very smart. And then x goes at the top right and then he gets a victory. Now we can enter any key to play again, or we can just press Z to exit. And that's all there is to it. It also detects if there's a tie game, and that all gets handled in the board, the actual checking of victory. So you can come in here and see how this works. Right now, it assumes that the board is always going to be a square, but it doesn't necessarily have to be 3 by 3. Now, in my game, it is going to be 3 by 3, but you guys can come in here and easily change that. If you want to have a board that's not a square, you're going to have to change this check victory function a little bit. Also, you'll notice the way I was drawing it is I was drawing these 3 by 3 glyphs instead of just a single X or O. I just think it looks better that way. It's easier to see. And if you want to see how that works, just go into the print function, and it should be fairly, well, it's not super easy to understand just because of all these loops, but I think it's not too bad. If you have any questions, of course, just let me know. Now what we are going to be implementing is this AI class. Now I've already made the class outline here, but it doesn't have any implementation. You'll see there's this AI perform move. Now this function already does get called if you select no for multiplayer in the beginning. And what it's going to do is it's going to call, if we go to the main game loop, it's going to check if it's not multiplayer. And if the current player is the AI player, then it's going to go ahead and do this AI move function. Now the AI move function calls AI.performMove, which we have to implement. So let's go ahead and do that. Go ahead and pause the video if you haven't already downloaded the source code and do that. Now the algorithm that we're going to be using for our AI is the Minimax algorithm. This is an algorithm that iterates every possible move and assigns a score to that move, and then it figures out which of those moves was the best move, whichever one had the highest score, and uses that move in the actual game. So I know you're thinking iterating all of these moves is really slow, and by the way, iterating every combination of something is also called enumeration. You'll see that word a lot. However, for tic-tac-toe, there's really not a lot of possible moves, so we can actually do this brute force iteration and it'll be perfectly fine. In fact, this website here that I will trust said that there is 255,000 total different possible games, and that's just going to be the worst case. If we decide that the AI wants to go first, he will have to check all of these different games and pick the best one. But that only happens if the AI goes first, and really 255,000 isn't even a lot of games computer-wise, because the computer is really, really fast. We can iterate through 255,000 different things really quickly, especially with optimization. Now, in debug mode, we don't have optimization, but we'll try it in release mode later, which does give us optimization, and see how that changes how fast it runs. But let's not worry about that for now. For now, let's just worry about what the algorithm actually is. So let's take this board state, for instance. This isn't the beginning of the game. This is kind of right at the end of the game. And this is a really easy board state for us to actually examine to see how this algorithm works. Now let's say that the X player is the AI player, meaning he went first. Now what he's going to do is he's going to try every single move that is possible for him and assign a score to each move. And whichever move is the best is the one that we take. So I'm going to use green X's and green O's to represent future moves. So let's say he starts by moving right here. First he's going to check this move. Now here's where we do the Minimax algorithm. After we place this X, what we're going to do is check and see what the score is of this move. Now if it resulted in a win, then we're going to give ourselves a score. So in this case we got 3 X's in a row and we're going to get a score. And Arbitrarily, you can pick plus 10. Plus 10 is a nice score for that. So now our score is plus 10 for this move. Now that means it's a really good move, and since we won the game, we don't have to go any deeper doing any recursion or anything like that. We can just stop here. So we know that this vertical move has a plus 10. Now let's try a different move. Let's try moving here. Well, if we move here, we didn't win, so we don't get plus 10. In fact, our score doesn't change at all. So what do we do now? We keep going. We recursively call the Minimax algorithm. However, it's not X's turn now. X just put his X right here. Now it's O's turn. So now we're pretending that O is the AI player, and he's going to place it wherever he wants. Now he might place it here, and nothing happens. There's no score change here, because what am I talking about? There is a score change, because he gets 3 in a row. Now, whenever O gets 3 in a row, we're not going to give a plus 10, we're actually going to give a minus 10. So this move right now has a minus 10 with O going here. Now if O instead tries to go here, that's also going to be minus 10. So what's going to happen here is O is going to say, which of these two moves is the best? Well, both of the moves give minus 10, and O is trying to get the lowest possible score since O wants to win. So what it's going to do is it's going to pick just one of the two. It doesn't matter which one since they're both negative 10. And that's going to be the score for this X move. It's going to be negative 10, because if you move here, O is going to win no matter what. So now this score has this move has negative 10, this move has positive 10. Obviously we don't want to do this move, we probably want to do this move, but let's see what happens if we do this final move down here. We put an X here. Well, we did block O here. However, now we have to do the recursion again and see what happens as O plays. Now it's O's turn. Let's say he places an O here. As we know, if he places the O here, that's going to be a minus 10. And if he places the O here, that's going to be 0. So let's assume that he places it here. We're on that iteration. Now nobody won, so we have to go even deeper into the recursion. So now we have to place another X. Now there's only one place to put the X, and this is going to be right here in the middle, which gives us 3 in a row in 2 directions. So this is going to be worth 10 points. Meaning that if O decides he wants to place here, that's a score of positive 10. So now we know that if it's O's turn, this is worth negative 10, and this is worth positive 10. However, since it's O's turn, he wants to pick the one that is smaller. So O is definitely going to pick this. Therefore, this move is worth negative 10. So this move is worth negative 10, and this move is worth negative 10. So this is the only move that we are going to want to do. It's this center move, and that'll cause the victory. And that's pretty much the entire algorithm. Now, if my explanation did confuse you, just check the description. There's a link to another guy's tutorial who goes through the exact same algorithm and tells you how it works. But for now, let's just go ahead and try to implement it. It's actually very simple. All right, let's come over here to the AI. Now, we're going to need some kind of struct or class to signify what a move is. So let's call it struct. We'll just say AI move. And it's going to have an int x, an int y, and an int score. Now we also need a function down here. We're going to say, we'll call it AI move get best move. And that's going to take the board, because we need to actually modify and look at the board. And it's also going to take the current player. So we're going to say int player. Now if you haven't already looked through the source code and you're not sure why we're using an integer for the player, if you go to board.h, you'll see I have these 3 constants for the indexes of the board. 0 means there's no player, x is 1, o is 2. So this AI player here and this human player are going to be either a 1 or a 2, 1 meaning x, 2 meaning o. So let's go ahead and implement this in the CPP file. This will be a recursive function that does the Minimax algorithm. Now the first thing we need to do is let's go ahead and loop through all of the different possible moves that we can actually do. And to do that, we're going to need to iterate through the board. We're going to say for, we'll start at y, int y equals 0, y is less than board.getSize, y plus plus, and it's actually board, not underscore board, and it's y, not I. And for int x equals 0, x is less than board dot get size x plus plus. Here we go. Now this will loop through the board. Since we are assuming that it's a square board, the width and height are both going to be size. And what we're going to do is check and see if the spot at this board is empty. So we're going to say if board.getVal, and this is going to be x and y. If that is equal to no value, that means it's empty and we can actually place a piece there. So that's one of the spots that we're going to need to check. Now what we're going to do now is create a move for this specific board spot. So we're going to say AI move, move, and this is the current move that we're looking at. Now the move.x equals x, the move.y equals y, and now what we need to do is actually get the score of this move. But to do that, we have to first actually place that imaginary x, that green x. And to do that, we're just going to actually place it and just remember to remove it later. So we're going to say board.setVal xy, and we're going to set it to the current player that is currently being, whose turn it is currently. I just said currently 3 times. All right, so there we go. That will set the value, and we have to remember to set it back to empty at the bottom here. If we don't remember to do that, then the AI will actually change the board and forget to change it back the way it was. So we'll change that to no val. Now in here is where we get the score. Now the way we're going to do this, I think the easiest way is we're just going to we're going to check if the player is AI or not AI. So let's go ahead and say if player is equal to AI player, else it's not the AI player. And what we're going to do is say move.score equals, and here's where we recursively call get best move. We're going to say get best move, and we're going to use the same board, but we're going to say what's the best move for the next player, which is going to be, if it's the AI player, it's going to be the human player. Otherwise, it's going to be the AI player, like that. So if the current player is the human player, we're going to check the best move for the AI player to get that score. Otherwise, we're going to check it for the human player. Now this returns a move, and a move also has an x and a y. However, when we're doing the recursion and we're going deeper, all we care about is the score of the next few moves. So we're just going to say dot score here. We're just going to get that score. Now this is going to be an infinite recursion because we don't have a base case. So let's put our base case here up at the top. And our base case is just going to check if there was a victory, if the game is over. So let's go ahead and call board.checkVictory. And let's go ahead and get the return value of that and store it. Now check victory returns 0 if it's a tie, 1 if X wins, and 2 if O wins. So let's go ahead and say if RV is equal to the AI player. Now remember, if the AI won, if the player who we're saying is the AI won, which could be X or O depending on what they pick in the beginning of the game, then we're going to go ahead and return a 10. Now we can't just return a score of 10, we actually have to return a move. So let's just go ahead and give our AI move a constructor, 2 constructors actually, a default one and one that takes a score. Int score, and that'll set score to score, like that. So now we can use this to just conveniently return the score. So AI move of 10, just like that. That will return a temporary AI move object. And we'll say else, and this is going to say else if RV is equal to the human player. Now remember, if the human won, that's going to be -10. So return AI move of -10. And remember, we don't need to set the X or the Y because all we care about is the score when we're doing recursion. And we can assume that we're not going to call get best move the first time on a board that's already complete, that's already finished, because the game would already be over. And else if RV is equal to, no val, which is just 0, then we're going to return AI move of 0. And that'll end the recursion. This is our base case. Base case, check for end state. Now let's go ahead and call these functions here before we forget. What we're just going to say is AI move best move equals get best move of board and AI player. So when the AI player performs move, he's just going to call this function. Now this base case is never going to happen the first time we call it. We're sure of that. And then finally we're just going to call board, underscore, or just board.setVal of bestMove.x, bestMove.y, and AI player. That's a very simple function. Alright, so now we're back to here. So that'll get us our score. So let's go ahead and look at an example and see how that's going to work. Let's say that the AI is looping through here, and it starts by just putting an X here. Well, when we call getBestMove on this move right here, we're going to come up here, and the base case is going to see that there is a victory, so it's going to return a positive 10. So the score for this move is going to be 10. However, when we go here, as we remembered, we're going to recursively call the same thing, and the score of this one or this one is going to be negative 10. Now we need to actually store this move, so let's get ourselves a vector, std vector of moves, AI move. That'll be moves. So we need to include vector here at the top. Alright, and now anytime we actually make a move, we're just going to push it back here. We're going to say moves.pushback of move. There we go. And finally, we're actually almost done here. It's like I said, it's very simple. Finally, we need to actually do the logic for picking which of these moves was the best one. And that's going to depend on if the player is the AI or the non-AI player. So if player is equal to AI player, else. Because remember, if the current player is the AI player, he's going to try to get the highest score. He wants to get positive 10. But if the current player is the human player, he's going to try to get negative 10. So let's go ahead and keep track of the best move, int best move, and we're going to say it's the 0 index into the moves vector is the best move at the start. And we'll change that inside these if-else statement. So let's say int best score. And we're going to go ahead and sentinelize this. We're just going to set it to a really, really small number, since the AI player is trying to get the biggest number, so that this will definitely get set to a any positive number or any negative number right off the bat. So for int I equals 0, I is less than moves.size, I++. It's going to loop through each of our moves. And what we're going to do is check if moves I, if it has a higher score, dot score moves I dot score. If that is greater than the best score, then we're going to say the best move equals I, and this will happen guaranteed at the very beginning at least once. And then we're going to say best score equals moves I dot score. By now you should know how to find the highest score in a list of scores. That's all this is doing. And now for the other case, whenever it's the human player, we're going to sentinelize it to a positive number, and instead of greater than best score, we're just going to do less than best score. That's the only difference. So this is going to pick the lowest score in the array, and this is going to pick the highest score in the array. Finally down here, we just return moves best move. And that's all there is to it. So let's go ahead and add some comments here. This is going to be do the recursive function calls and construct the moves vector. Pick the best move for the current player. And finally, return the best move. Alright, so that should be it. I think it's going to work. Let's go ahead and run it. Now multiplayer, we're going to say no, so we're going to be playing with an AI. Now I want to be X. I'm going to go in the middle, and we get vector subscript out of range. Let's hit retry and see what's going on. So where I'm calling board.setVal, that seems to be where the issue is. I'll go ahead and pause the video and figure out what's going on. Sorry, it was actually a very simple mistake. It doesn't return 0 when it's a tie game. It actually returns tie val, which is -1. What was happening here is exactly what I said wouldn't happen. is this base case was happening at the very beginning, which means this best move just had uninitialized x and y values, which caused the crash. So now it should work. Let's go ahead and run it and see. Multiplayer, no. I'm going to be x, and I'm going to place it in the middle, and O places at the bottom left. And now it's my turn again. I'm going to place, let's go ahead and do 1, 2. And as you can see, O immediately blocked me. And let's play stupid. Let's see if O will win. I'm going to go 3, 3. And O goes at the bottom left. And then I'm going to go 2, 3. And O goes at the bottom right. It played perfectly, and it won the game. And that's all there is to it. That's our recursive AI using the Minimax algorithm. Let's go ahead and play again. No, not multiplayer. This time I'm going to be O, which means he's going to go first. And just watch how long it takes to actually calculate all of the possible moves. And see, that was a couple seconds. That was pretty long. Now that's the worst case scenario, because the next time I play something, it's almost instant. Now let's see what happens if we compile in release mode. It should be a good bit faster. Now release mode optimizes your program. The compiler actually does a lot of really smart tricks behind the scenes and removes some debugging code. So multiplayer is going to be no. I would like to be O. And let's see how fast. It's much faster. It's almost instant. It's less than a second. And everything else is definitely going to be instant. Now there's a few ways you can improve this. You could try to make it so that the AI isn't perfect, so that you could select different difficulty settings. Now if you wanted to make it so that the AI isn't perfect, what you could probably do is just add random values to the score. And you know, depending on how dumb the AI is, the bigger or smaller the random values are. And also another thing is this program has an AI that is fatalistic, which means if you give it a board that is already kind of not perfect, not perfectly played by the AI, say if we forge a board and we just give it a board state and get it to perform on it, what it's going to do is it's not going to care if it loses now or loses later. If it knows it's going to eventually lose, it'll just lose immediately. Now, if it's playing a human and not a perfect player, that's not the optimal strategy, because the human may not play perfectly and may not actually win, even though the AI thinks it's going to lose. And there's actually a way to solve that using depth. You can make it favor depth. And if you look in the description, I will give you a link to this awesome website that talks about this entire algorithm and actually goes into how to make it non-fatalistic by using the depth. Now hopefully this didn't confuse you too much. If you have any questions, I'm always available in the comments, so just go ahead and leave a comment and I'll help you out. Thanks guys.